As we begin looking at different types of reactions, the first one we're going to take a look at is what's known as a synthesis, or also known as a combination reaction. The identifying trait or characteristic of a synthesis or combination reaction is we have two or more reactants combine to make a single product, would be the identifying feature of a synthesis or combination reaction. So what we would see is we have a reactant A, a reactant B for two different reactants, and they're going to come together and make a single product. And that would be our identifying feature again of a synthesis or combination reaction. Our first example is we have a metal combines with a nonmetal to form a binary salt. A binary salt, that's another way of saying we're going to make an ionic compound. So we remember an ionic compound is a combination of a metal with a nonmetal. For example, if we were to take elemental sodium, react it with chlorine gas, that would combine, go through a synthesis reaction, and make regular old table salt, sodium chloride. We would then balance the equation, make our atoms the same. Since we have two chlorine atoms here, we need two on the product side. And then we balance it with our two sodiums here. And we now have a balanced combination or synthesis reaction. Let's do another example. We have lithium metal being dropped into a container of nitrogen gas. Lithium would be Li. Nitrogen gas, being a Hunkelbrief, is N2. Now when this comes together, it's going to turn into ions. So to get our compound correct, let's write out lithium as a 1 plus ion, and then nitrogen makes nitride, which is N3 minus. So the compound we're going to make, lithium nitride, will be Li3N, would be our product. We now balance the equation by placing a 2 in front of the lithium nitride. That balances, we have two nitrogen atoms on both sides. And now we have 6 lithium, so we put a 6 over here by the lithium, and our equation is now balanced. This would be another example of a combination reaction. Our next combination reaction is we have metallic oxides. Metallic oxides will combine with water and form bases. Specifically, we'd say they are metallic hydroxides would be our bases. Our first example, we have sodium oxide. Now, sodium is a 1 plus ion, oxide's a 2 minus, so the formula of this would be Na2O, would be our sodium oxide. That combines with water, and this is a metallic oxide because sodium is a metal atom, and it's combined with oxygen. When a metallic oxide combines with water, we make a metallic hydroxide. A metallic hydroxide would be a base. Now, a metallic hydroxide, because our metal here is sodium, we're going to have a sodium ion and a hydroxide ion, so our product would be NaOH for sodium hydroxide, and that would be our metallic hydroxide or base that gets formed in this combination or synthesis reaction. Placing a 2 in front of the NaOH balances the equation. That gives us 2 sodium atoms on both sides of the equation. We have 2 hydrogens and 2 oxygens also on both sides of the equation, balancing it for us. Let's do another example. Here we have solid magnesium oxide. Now magnesium is Mg2 plus, oxygen's 2 minus, so magnesium oxide will be MgO. We're going to add that to water. Since magnesium is a metal, we've got to combine with oxygen here in a compound. That's a metallic oxide. We're mixing with water. This is going to make a metallic hydroxide or a base. To figure out our metallic hydroxide, the metal is magnesium. Magnesium is Mg2 plus. Hydroxide is OH1 minus. So our metallic hydroxide here is going to be Mg parentheses OH2 to make our magnesium hydroxide product in this combination reaction. This equation, it turns out, is balanced as written, so we need to do no further to balance the equation. Our next example of a combination reaction is a category that non-metal oxides and water form acids. Now if we consider this, a metallic oxide and water formed a base. A nonmetal is chemically the opposite of what a metal is, and here we have a nonmetallic oxide and water will combine to form acids. Specifically, something known as oxyacids get formed by this combination. An oxyacid is specifically an acid where the compound contains an oxygen. For example, HCl, hydrochloric acid, is not an oxyacid. H2CO3 is an oxyacid. HCN is not an oxyacid. H2SO4, sulfuric acid, is an example we would categorize as an oxyacid compound. Now in this particular combination reaction where nonmetal oxides and water form acids, a key component is that in the reaction the nonmetal is going to retain or keep what's called its oxidation number. And the oxidation number stays the same as we move from reactant to product. We have to take a minute now to go through how does one determine exactly what the oxidation number is for a particular atom in a compound. Take a moment and go through the rules that are utilized to assign oxidation numbers to atoms and compounds. Our first rule is an atom of any element in its naturally occurring form has an oxidation number of 0. So all of these here, if we have something like elemental iron, O2, bromine, these are all the natural elemental forms of these elements. They have an oxidation number of 0. In their naturally occurring elemental form. Our second rule, if we have something that's a monatomic ion, the oxidation number is the same as the charge on the ion. So something like Na1+, which is a monatomic ion, it has an oxidation number of +1. Or if we had, say, Mg2+, since that's a 2+ ion and it's a monatomic ion, its oxidation number is +2. Our third rule is that fluorine, which appears quite commonly in covalent compounds, it's assigned an oxidation number of -1 when it's in compounds. So if we have something such as xenon difluoride, the individual fluorines in this compound each have an oxidation number of -1 that's been assigned to them. Now another element, because it appears so commonly in compounds and is assigned an oxidation state, is oxygen. Oxygen typically has an oxidation number of -2 when it's in compounds. So if we have something like H2O, water in this compound has an oxidation number of -2. Or if we have something, a covalent compound, CO2, likewise, oxygen in the compound, an individual oxygen, has an oxidation state of -2 in this compound. Now, of course, chemistry wouldn't be chemistry without some exceptions, and that is oxygen has an oxidation state of -2 when it's in a peroxide, which is H2O2 is hydrogen peroxide. In this compound, oxygen's oxidation state is -1, and that's our only exception for oxygen. Hydrogen is also assigned a value for an oxidation state. Hydrogen has a value of +1 when it's in a compound. So if we see something like, say, NH3, a covalent compound, the oxidation state of hydrogen atoms in this compound have a value of +1. Or if we have something like methane, CH4, likewise, the oxidation state of an individual hydrogen atom is +1. We have two more rules with our oxidation numbers. And that is, if we have something that's a neutral compound, all the oxidation states need to add up to equal 0 in that compound. For example, methane. Hydrogen is assigned a value of +1 per each hydrogen. Since there's 4 hydrogens, 4 times +1 gives us a total of +4 for all the hydrogens for their oxidation state. Since this compound is neutral, that means the individual carbon atom here has an oxidation state of -4, or that would be the oxidation number assigned to carbon in this compound. Now, if we have something that's a polyatomic ion, the oxidation states in that compound need to add up to equal the charge on that particular ion. For example, we have carbonate. Now, oxygen in a compound is assigned an oxidation state of -2. Since there's 3 oxygens, 3 times -2 gives us an oxidation total for oxygen of -6. Now, everything has to add up to equal -2 in this compound. Because the oxygen has a total of -6, that means the carbon in this compound has an oxidation state or oxidation number of +4. Then that +4 plus the -6 for the oxygens add up to equal -2, which is the charge on this polyatomic ion. Let's do an example of this type of combination reaction. Our first one here, we have carbon dioxide is bubbled into water. Now as we look at the reaction, carbon dioxide is something we categorize as a nonmetallic oxide because carbon is a nonmetal and it's in a compound with oxygen. Nonmetallic oxides and water will combine to make something known as an oxyacid. Now the thing with carbon dioxide combining with water is there's two different oxyacids that are possible. We have carbonic acid and also oxalic acid. To determine which is the correct product, we have to determine the oxidation number of carbon in the carbon dioxide and see which one, carbonic acid or oxalic acid, does the oxidation number of the carbon remain the same, and that would be the correct product. So as you look at the carbon dioxide, again, oxygen has an oxidation state of -2. Because there's two of them, the total for the oxygen is -4. This is a neutral compound, so that means the carbon in CO2 has an oxidation state or oxidation number of +4. We now want to see of the two products, in which of them does carbon have an oxidation state of +4, and that would be the correct product in this combination reaction. As we do the carbonic acid, oxygen has an oxidation state of -2. There's 3 of them times -2. That gives us a total of -6 for the oxygens. Hydrogen is assigned a value of +1 for an oxidation state. 2 of them gives us a total of +2. This compound is neutral, so everything has to add up to equal 0. So that would mean carbon in this compound has an oxidation number of +4. Let's repeat the process for the oxalic acid. Oxygen has an oxidation state of -2. There's 4 oxygens, so that's a total of -8 for the 4 oxygens. Hydrogen is assigned an oxidation state of +1. There's 2 of them, hydrogen, so that's a +2. We have 2 carbon atoms in here. The total has to be a +6 for the 2 carbon atoms. So that means individually the carbon, since there's 2 carbon atoms and our total is a +6, that means individually each carbon atom would have an oxidation number of +3. Now as we look at the 2 compounds here, the correct product is the one where the oxidation number of the nonmetal remains the same in the oxyacid that's formed. Since oxalic acid's carbon has an oxidation state of +3, that one's out. The carbonic acid, the carbon has a +4 oxidation state. That's our correct product in this combination reaction. Let's do another example. Here we have dinitrogen pentoxide. Nitrogen is, again, since nitrogen is a nonmetal and it's with oxygen in a compound, this is a nonmetallic oxide combining with water. We're going to form some type of oxyacid as a product, and the correct product, the oxidation number of nitrogen, will remain the same in the product as it was in the reactant. In this case, 2 possible oxyacids can be made. We have HNO2 or HNO3. We need to identify which one has the same oxidation number for nitrogen as in our reactant dinitrogen pentoxide. In dinitrogen pentoxide, oxygen again has a state of -2. There's 5 of them times -2 gives us a total of -10 for all of the oxygens. This is a neutral compound, so all the nitrogen is +10. Because there's 2 nitrogen in this compound, individually nitrogen has an oxidation state of +5. We now need to see which product does nitrogen also have a value of +5 for its oxidation number. When we identify the oxidation number of an individual nitrogen atom in each of the products, it's found the HNO3, the nitrogen has an oxidation number of +5, making that the correct product. The HNO2 nitrogen has an oxidation state of +3. That would not be the appropriate product for this particular combination reaction. One last type of combination reaction is we have metallic oxides and non-metallic oxides combined to form salts. Salts are another way of saying that they combine to make an ionic compound. In our first example, we're going to take solid sodium oxide and add it to carbon dioxide. Now, typically what happens there, when come together and make one compound as a product, because it's a combination reaction, a common carbon-containing polyatomic ion is carbonate. These come together to make the salt sodium carbonate. And then this equation is balanced as written. Here we have another example. We have metallic oxide, calcium oxide, a non-metal oxide, sulfur trioxide. They're going to come together and form the salt calcium sulfate. And then this reaction is balanced as written.